Schematic symbols and pilot devices. In this presentation, we're going to be looking at push buttons, timed contacts, other pilot devices, pilot device operation, and wrapping it all up with maintain switches. Let's get going. Push buttons come in a variety of different shapes and sizes, and we need to know what the schematic symbol looks like. Schematic symbols are always shown in their normal position, and a push button being a momentary contact device means that it will return to the position that we see shown here on the page after it has been released by our finger. We have normally open, normally closed, double circuit, which would then mean 4 terminals. And when we press the plunger down, this top 2 terminals would break and the bottom 2 terminals would make. Mushroom head, which is just a fancy term for a big old red head, normally closed push button, and 2 single circuit. This is indicating the exact same push button as this one here, the double circuit, the difference being that they're showing the top portion and the bottom portion in 2 different places within the circuit. So at times you'll see a dotted line connecting them together, and that to us then means that it is the same object or same push button mechanism that is in 2 different places. Here's a few snapshots of push buttons, pretty exciting. And we can see on the left-hand side is more of a self-contained type of assembly where they got the normally open, normally closed contacts that are actually screwed in there. And then on the right-hand side, we see more of a modular setup. The red little square here is indicating a normally closed contact, and the green is a normally open. And the push button assembly on the top makes contact with them by pushing them down. And the contacts then change state. So for this particular push button assembly, we actually have 2 contacts for each push button. Timed contacts are controlled by timer relays. And the typical contact functions that we see for timed contacts are on delay, off delay, one shot, interval, and there are many, many others. On and off delay are the most widely used timer functions in the electrical industry. And so we need to have a fairly good idea as to how they function. TDOE is time delay on relay coil energization. There are normally open and normally closed. Often you'll see them represented here with a little arrow, and that indicates that it's a timed contact. The one on the left says NOTC, and that acronym stands for normally open, timed to close. On the right side, we see NCTO, which is normally closed, timed to open. So how do they function? Let's take a look. We've got a TDOE relay coil on the left-hand side. I've got a stopwatch in the middle, and then the contacts that the coil are controlling are located on the right-hand side. When I close the switch, the timer should start. So let's see what happens. The timer is now timing, and as soon as the time has concluded or elapsed, the timed contacts open and close, depending on what their original normal state was. When I de-energize the coil, there's no time delay, and the contacts go back to their normal state. By contrast, a TDOD is a time delay on relay coil de-energization. We have normally open and normally closed. NOTO on the left side means normally open, timed to open. And NCTC represents normally closed, timed to close. So let's see how this one functions. Same idea. We've now got a TDOD relay coil, and the contacts that it will control are on the right-hand side, and we can always distinguish between TDOE and TDOD contacts by the way in which the arrows are facing. So let's close the switch and see what happens. Immediately, once I energize the TDOD coil, the relay contacts change state. They're instantly changing state because there is no delay on energization with a TDOD relay. When I de-energize this coil, there will be a measured amount of time of delay before these contacts go back to their normal state. So let's open the switch and de-energize the relay coil. Going through the timer function, and once the time has elapsed, the contacts go back to their original state. There are many different types of pilot devices. We have vacuum and pressure switches. So some of them work on negative pressure, others on positive pressure. We have normally open and normally closed. These are examples of different types of pressure devices that can either be triggered at varying levels of suction or pressure or a set value. We have liquid level switches, often known as float switches. Again, normally open or normally closed. This is what they typically look like on the end of a long piece of cab tire, and they simply float in the medium or the liquid that we are attempting to measure. And as the liquid gets higher, the float moves up, and we can see here from the ball that is in the yellow chamber on the right-hand side, that is what moves the contact. So its orientation from vertical to horizontal will make a difference. And so we can use this to control motors and all sorts of other different items. We have temperature actuated switches, again, normally open or normally closed, and those often can be in the form of either pressure sensitive or rather temperature sensitive instant switches that we see at the very bottom where they simply actuate at a particular temperature, or thermostats like for a baseboard heater, or different items that have a probe, and we put the probe into the area that we want to measure the temperature for, which we see on the left-hand side. Now, with all of these, it should be known that if we go back to pilot devices here, that all of these are actuated by an increase in value. So whichever one we're discussing right now, if we see an increase in pressure, this will close. If we see an increase in pressure on this one, it will open. If we see an increase in liquid level, this will close. Increase in liquid level, this one will open. Increase in temperature, this one will close. Increase in temperature, this one will open. So it's important to understand that the operation of the pilot device is consistent with an increase in value, and they simply move in the direction that we would then anticipate physically on the schematic symbol itself. We also have things like limit switches, which are used in conveyor systems and all over the place to make contact with a mechanical or object of some sort. Pretty simple operation. We have flow switches, which are used to determine if there is flow of liquid inside a pipe. That flapper that we see at the very bottom, this one on the right is more of a brass color, this one's plastic, is actually inside the pipe. And when water flows through the pipe, it would push this small little flapper, and the flapper would then actuate a set of contacts in the main control box at the top. There is very little resistance that is offered by this little very thin metal flexible flap, and so it does not impede the flow of the liquid inside the pipe. And we have things like foot switches, and this is used for different types of mechanical machine operation where we need to ensure that we have control of the object with our feet instead of hands, because the hands are doing something else on the equipment. Finally, we have things called proximity sensors. Now, proximity sensors come in normally open or normally closed, and they're considered non-contact devices. So here's a selection of different proximity sensors, and we're going to take a look at the two very most common that we see out in industry. Proximity sensors are non-contact, and that simply means that there's no physical touch with the object. Instead, the object simply has to be close. We can use it in all sorts of different ways to sense when there are things on conveyor belts and how many things are on conveyor belts. We can count things. We can also use it to determine liquid level by putting proximity sensors on the outside of a container. And then when the liquid reaches the level of the sensor head, it triggers it. Capacitive proximity sensors are one of the two most common that we see out in industry. They're an on or off device. Medium density objects work best, and they are an adjustable device. Usually you can tell that it's capacitive by it having a yellow or orange sensing head. What's unique about a capacitive proximity sensor is that it's really just triggered by the density of the object it's sensing. So it has nothing to do with it being metal or water or dirt or any of that. It's simply how dense the object is. Inductive proximity sensors, by contrast, are a little bit different. They're on or off, but they really only detect the presence of ferrous metals. So think of it as a metal detector. It's got a much further sensing distance than capacitive, and typically these have a blue sensor head. Now, these are far less expensive than capacitive. Capacitive are very expensive sensors when compared to an inductive proximity sensor. Photobeam sensors. This is another type of non-contact sensor, and the contact that we see, or the item that's controlled, the schematic symbol, would be a standard set of normally open or normally closed contacts. Now, a photobeam sensor typically has a receiver and an emitter and a reflector lens, and the principle of operation is quite simple. The emitter emits a photo beam of some sort, and there are many different types, out to the reflective lens, and the lens is positioned in such a way that the beam can then be bounced back to the unit, and the receiver receives the signal. If the beam is broken, the photo beam sensor then indicates this by changing the state of the contacts. There are many different types of photoelectric sensors in the electrical industry. Some are designed for sensitivity to horizontal motion, others to vertical motion. Some require a reflective surface to bounce the beam back, others do not. There is a dizzying array of different types of sensors and the different applications they serve. There are many types of photosensors that are also used to extrapolate more than just the presence or no presence of an object, but instead to analyze the object and determine further parameters on it, such as in this little animation here. A very common example of a very basic photosensor is usually mounted at the base of the garage door opening for a standard residential overhead garage door. When the beam is broken and the garage door is traveling in the down direction, the door should automatically stop and reverse direction so that it goes back to the fully open position. Pilot device operation is fairly simple, and it's good to just have a bit of an animation to see how the system works. Remember, we said the schematic symbol always moves in the direction that the medium is traveling. So increase in liquid would mean an increase, and the float switch would then rise. A normally open float switch will close on a rise of liquid, and we can see here again that as the liquid rises, the float switch goes to a closed position. Now we can also use float switches and different pilot devices in a held position. So this one is held open, which means it's going to close on a drop of liquid. So this is a normally closed float switch. As the liquid level drops, the pilot device goes back to its normal position. So it's not really different, I suppose, than the first one we looked at, but it is a little bit of a different application. Again, we could have a normally open float switch, which is held closed and it opens on a drop of liquid. As the liquid decreases, the pilot device goes back to its normal position. When we look at pressure switches, same idea. They open on a rise of pressure if it's normally closed, and normally open pressure switch would then close on a rise of pressure. Again, just like the other application, we could have a pressure switch in there that's held closed. So it's a normally open pressure switch and it opens on a drop of pressure. And this might be advantageous for a system where we want to be alerted if the pressure in the system drops below a predetermined level. Maybe an alarm goes off. If we place the pressure switch in like this, as the pressure decreases, the pilot device goes back to its normal position and perhaps an alarm is then initiated. We could also do a normally closed pressure switch held open again, and this would close on a drop of pressure. As the pressure decreases, again, the pilot device goes back to its original position. Any pilot device can be used in both ways, either normal or held, and it's good to understand that this is a possibility out in the electrical field. Also, many pilot devices will come with both normally closed and a normally open contact with a common terminal. And in this way, you have the option of using the normally open or the normally closed. Maintained switches are an item that we see all over industry, and it's good to understand what some of the abbreviations are that are given and the acronyms. We have SPST, which would be single pole, single throw, SPDT, single pole, double throw, DPST, double pole, single throw, and finally DPDT, double pole, double throw. So there are different applications for each one. What is important about a maintained switch is that it remains in the position that you push it to physically. There is not a spring that locates it in a normal quote unquote position. Instead, either position could be its remaining or standard position.